Located just 4.24 light-years from Earth, the closest exoplanet with the potential to support life ever discovered by humanity. It possesses remarkably Earth-like characteristics. And most importantly, it lies within the habitable zone, orbiting the red dwarf star Proxima Centauri. We are talking about Proxima b. As a primary target for interstellar research, astronomers around the world are working to answer a fundamental question: what awaits us on Proxima b? Could life exist there? A distance of 4 light-years is an enormous barrier, so vast that by the time you returned, Earth itself might have completely changed. And that is only the beginning of the challenges. Will we one day overcome these barriers? Or will Proxima b remain a distant dream? Let us explore the mysteries and obstacles that Proxima b presents to humanity. Proxima b, with an estimated size about 1.17 times the radius of Earth and gravity roughly 1.3 times our own, is almost a physical twin. This level of gravity is considered ideal for supporting the development of macroscopic life without causing radical biological changes. If Proxima b contains sufficient water, this gravity would allow liquid water to persist on its surface and could enable life forms to develop with relatively familiar morphologies. But does similarity in gravity guarantee habitability? When the environment is dominated by a completely different star? Although the planet sits neatly within the habitable zone of its parent star Proxima Centauri, the harsh reality lies in the nature of the star itself. Proxima Centauri is an M-tabletop red dwarf. Red dwarfs are known for their stability over trillions of years, but are incredibly volatile over short periods. Because Proxima Centauri is much dimmer than our Sun, Proxima b must orbit extremely close to receive enough heat to maintain liquid water. This proximity results in tidal locking. One side of the planet is permanently baked in daylight, while the other side is locked in eternal night and freezing temperatures. The greatest danger is not temperature, but radiation from stellar flares. Red dwarfs frequently release violent bursts of extreme radiation, hundreds of times stronger than any solar storm. These flares emit ultraviolet and X-ray capable of gradually stripping away atmospheric layers, especially lighter gases like hydrogen and helium. This radiation threatens surface life unless the planet possesses an exceptionally strong planetary magnetic field like Earth's protective shield, or unless life has evolved to survive deep underground or underwater. Proxima b's atmosphere must be thick and stable enough not only to redistribute heat from the day side to the night side, but also to withstand the destructive power of periodic radiation storms. Can a tidally locked planet bombarded by intense radiation retain sufficient oxygen, carbon dioxide, and water vapor to create a habitable environment? Or has it long since become a barren, lifeless world? This is the question next-generation telescopes are trying to answer. It is our most feasible interstellar destination, yet it lies 4.24 light-years away. This distance is 250,000 times farther than Earth is from the Sun. This immense gap is both a measure of current technological limits and a driving force behind breakthrough concepts such as solar sail spacecraft or antimatter engines. Proxima b represents the most compelling invitation in the universe, but can we invent something capable of surpassing the 76,000-year threshold and make this place the first stepping stone for humanity among the stars? To turn Proxima b from a distant speck of hope into an actual destination, we must overcome physical and engineering barriers that seem insurmountable. This isn't about small incremental improvements. It demands a leap in physics, a revolution in speed and energy unprecedented in the history of science. Humanity's current achievements in space travel, incredible within the solar system, are rendered almost meaningless when faced with interstellar distances. We have reached the limits of chemical propulsion technology, burning fuel and expelling hot gases backward, essentially launching enormous bullets. When it comes to traveling to Proxima b, current spacecraft speeds and energy capabilities are far from sufficient. Voyager 1, the fastest spacecraft humanity has ever built, travels at 17 kilometers per second. Even though it has been moving since 1977, it would take 76,000 years to reach Proxima Centauri, where Proxima b orbits. This starkly illustrates that current space travel technology cannot meet the requirements of interstellar travel. Proxima b will remain out of reach for thousands of generations unless we radically transform propulsion technology. So why not just build a bigger chemical rocket? The Sikorsky rocket equation shows that reaching near-light speeds would require a spacecraft to carry fuel millions of times its own mass. And this leads to an insurmountable problem. The fuel itself would need more fuel to propel it, creating an endless, unworkable cycle. Conventional chemical rockets will never suffice to reach Proxima b. We need a completely new way to generate thrust, a leap in physical technology. The breakthrough Starshot project offers a bold solution. Starshot proposes separating the propulsion source from the payload. Rather than a heavy craft, we could use grand-scale micro spacecraft attached to ultra-thin light sails. The thrust would come from photons concentrated by a colossal laser array capable of delivering up to 100 gigawatts. Photon pressure, small but continuous, would accelerate the light sails and star chips to incredible speeds, 20% the speed of light, about 60,000 kilometers per second. At this velocity, the journey to Proxima b could be shortened to just 20 to 30 years, a feasible time frame within a human lifetime. Yet breakthrough Starshot faces enormous technical challenges. The light sail must withstand extreme accelerations from the intense laser beam and endure the extreme heat of the interstellar journey. It must survive roughly 20 years in the harsh environment of interstellar space, exposed to cosmic radiation and extreme conditions. The laser's precision must be maintained at an extraordinary level. Even a tiny deviation in targeting a sail, just a few square meters in size, could doom the mission. While Starshot offers a glimmer of hope, the energy challenge remains colossal. Reaching 20% of light speed, even for a craft weighing only a few grams, requires an immense amount of energy, millions of times what humanity can generate in a single instant. Achieving this with 100 gigawatts is not only a technological challenge, but a global energy infrastructure problem. We cannot rely solely on existing terrestrial power sources. Directed energy technology, transmitting power from a single point on Earth to a distant spacecraft without onboard fuel, is the most practical solution. Humanity needs a revolution in how we generate and use energy. If we can clear these barriers of speed and power, the journey to Proxima b becomes imaginable. But the ultimate question remains: do we have the capability and will to build a global energy infrastructure capable of sending a tiny emissary across 40 trillion kilometers? Can we unlock the mystery of Proxima b in a few decades instead of 76,000 years? The journey to Proxima b presents unprecedented challenges for human health and psychology. A centuries-long voyage requires confronting issues never before encountered in history. From the physiological effects of microgravity to extreme psychological stresses of living in a confined, isolated environment. Beyond that, maintaining life on board for such an extended period demands sophisticated solutions for food, water, and air supply. These factors affect not only biological functioning, but also survival and mission success. This journey could span centuries. Microgravity directly impacts human organs and physiological systems. Studies show that in weightlessness, the body undergoes dramatic changes, particularly in bones and muscles. Without gravity to stimulate the body, muscles gradually weaken and lose mass. Similarly, bone density declines rapidly, leading to osteoporosis. NASA research in 2017 found that astronauts on extended missions can lose 2 to 3% of bone mass per month, significantly increasing the risk of fractures and musculoskeletal issues. Additionally, microgravity alters cardiovascular function. It also affects the nervous system, causing spatial disorientation, dizziness, and motor coordination difficulties. To counteract these effects, current space programs employ in-space exercise routines and support devices to help astronauts maintain physical health. However, these measures cannot fully prevent the deterioration of the human body in microgravity. Psychological challenges are equally formidable. Loneliness in deep space is unavoidable. This feeling can induce severe stress, impair teamwork, and compromise decision-making. NASA has conducted extensive studies on the psychological effects of long-duration missions, including the notable Mars 500 experiment. In this program, crew members lived in a Mars flight simulation for 520 days. Results revealed a marked increase in stress levels and psychological difficulties when social interaction was limited and when facing uncontrollable situations. Another crucial challenge is the sustained supply of food, water, and air throughout the voyage. Traveling decades away from Earth necessitates self-sustaining systems capable of recycling and producing these essentials. Such systems reduce reliance on Earth-based supply chains and ensure astronauts' autonomy in life support. Current self-sustaining technologies, such as those tested on the International Space Station, can recycle water and air from crew exhalations and sweat. Yet long-term food production remains a complex challenge. NASA is exploring space agriculture technologies, enabling astronauts to grow vegetables and crops in small onboard garden areas. However, maintaining a fully operational life support system that produces food, recycles water and air, and serves the entire crew over a centuries-long journey presents immense challenges. Human waste must also be managed effectively to protect health and maintain a clean, habitable environment aboard the spacecraft. The journey to Proxima b presents unpredictable hazards from space radiation, meteoroids, and other celestial debris. Each of these threats jeopardizes astronaut survival. Making interstellar travel a high-stakes endeavor. You must examine in detail the dangers posed by cosmic radiation, meteoroids, and space objects, alongside protective strategies designed to ensure human survival during this voyage. Space radiation, primarily galactic cosmic rays, GCRs, and solar radiation, represents one of the gravest threats to astronauts on long-duration missions. GCRs consist of subatomic particles and atomic nuclei, mostly protons with heavier nuclei such as helium and carbon, accelerated close to the speed of light by supernovae and other cosmic events. These particles are accelerated close to the speed of light by supernovae and other cosmic events. These particles carry enormous energy, capable of penetrating spacecraft shielding and inflicting severe biological damage. GCRs can pass through thick spacecraft materials, generating secondary particle showers upon impact. These secondary particles carry energy far exceeding the original, creating a complex radiation field that is extremely difficult to shield against. They also affect the nervous system, potentially causing cognitive impairment, memory loss, and motor coordination disorders. NASA and other research institutions have demonstrated that traditional materials such as aluminum or steel cannot fully protect astronauts. They may even exacerbate the problem by generating secondary radiation. Feasible alternatives include hydrogen-rich materials like polyethylene, water, or crew waste. Hydrogen is effective at absorbing high-energy particles, However, building sufficiently thick shields significantly increases spacecraft mass, conflicting with projects like Starshot, which require minimal weight to achieve extreme velocities. Another proposed solution is an active plasma magnetic shield. Using strong magnetic fields to deflect incoming particles. Though this technology remains in theoretical modeling stages. Solar particle events, SPEs, can pose another critical threat. Solar flares can eject vast amounts of protons and heavy ions into space, creating intense energy storms. These proton storms are thousands of times more dense and energetic than normal background levels, traveling at up to 10% of the speed of light. These particles can penetrate nearly all conventional shielding. Countermeasures against SPEs require both passive and active protections. One essential strategy is space weather forecasting, enabling early detection and warnings of high-energy solar events. spacecraft must also include a storm shelter, a specialized, heavily shielded compartment where crew members can seek refuge during predicted SPEs. The shelter could use thick layers of water or fuel to maximize radiation absorption and protect astronauts. In addition to radiation, one of the greatest physical threats comes from meteoroids and space debris. These objects travel at extraordinary speeds and can cause catastrophic damage upon collision. Even tiny dust particles impacting a spacecraft traveling at 20% the speed of light release tremendous energy, effectively acting as high-speed bombs. Such impacts could rupture the hull, compromise shielding, or destabilize ultralight spacecraft. NASA studies in 2018 confirmed that even minuscule, high-velocity collisions in space can inflict serious damage. While current research and technology are still developing, innovative solutions such as plasma magnetic shields, multi-layer protection systems, and self-repairing materials offer hope for long-term interstellar missions. Ultimately, continuous technological innovation will determine the survival of astronauts and spacecraft against both physical hazards and radiation on this extraordinary journey. In the grand journey of exploring the cosmos, Proxima b emerges as an alluring destination. Yet, reality paints a stark picture. Reaching this planet is nearly impossible. The staggering distance of 4.24 light-years between Earth and Proxima b presents immense technological and temporal challenges. Even at the maximum speeds humanity can currently achieve, the journey would span tens of thousands of years, making interstellar travel infeasible within a single human lifetime. Moreover, the environmental conditions on Proxima b remain shrouded in mystery. While the planet lies within the so-called habitable zone, the presence of liquid water and a stable, life-supporting atmosphere has yet to be confirmed. Factors such as radiation from its parent star, Proxima Centauri, may further jeopardize the potential for life. Though Proxima b offers a tantalizing glimpse of another world, the physical, environmental, and societal barriers remind us of a sobering truth. Reaching this distant planet remains a dream far beyond our grasp. Humanity's quest to explore the universe will continue, but perhaps our focus should first be on safeguarding and understanding our own planet before we reach for distant horizons. If Pluto is humanity's final frontier within the solar system, where sunlight fades and time grows dense, then the exoplanets beyond, the worlds never seen by the naked eye, are invitations to a farther horizon of understanding. Out there are no planets orbiting the sun, no familiar rules of light, temperature, or life. Instead, there are countless possibilities, other forms of being in the universe, where everything we know about physics, chemistry, and even existence itself is put to the test. Since the mid-1990s, when Michel Mayor and Didier Queloz discovered the first planet outside our solar system, 51 Pegasi b, humanity officially stepped out of its own shadow. That planet is a hot Jupiter. As massive as Jupiter, but orbiting so close to its parent star that 1 year lasts only 4 Earth days. Its atmosphere boils, with winds reaching thousands of kilometers per hour. From that discovery, a new era began. Thanks to the Kepler Space Telescope, launched in 2009, humans for the first time looked into the darkness between the stars. Kepler observed more than 150,000 stars, and to this day astronomers have confirmed over 5,600 exoplanets, worlds orbiting other suns. There are planets where glass rains from the sky, such as HD 1897-33b, where the blue shimmering atmosphere hides winds blowing at 7,000 kilometers per hour, flinging molten glass shards sideways like knives. There are planets as black as coal, like Tres 2b, absorbing 99% of all light, rendering them nearly invisible even next to a blazing star. And there are worlds where iron condenses and falls as rain, like WASP 76b, where day and night are eternally divided. One side burns at 2,400 degrees Celsius, while the other lies in endless darkness. The universe seems to be taunting human imagination. It creates worlds that should not exist, yet somehow they do. And yet, among all those impossibilities, there are planets that leave scientists breathless. Not because they are strange, but because they are familiar. In 2016, the ESO telescope in Chile discovered Proxima Centauri b, a rocky planet orbiting the star closest to Earth. just 4.24 light-years away. It lies within the habitable zone, a region where water could exist in liquid form. A world that might have oceans, an atmosphere, and perhaps life. The news was shocking, but the truth is harsher than imagination. Even though it is close, only 4.24 light-years away, that distance equals more than 40 trillion kilometers. With current technology, humanity would need over 80,000 years to reach it, even aboard the fastest spacecraft, New Horizons. We can see it, calculate its orbit, yet never touch it, though humanity conceived even more audacious ideas. The breakthrough Starshot project, initiated by Stephen Hawking and billionaire Yuri Milner, proposed using ground-based lasers to propel light sails, tiny spacecraft weighing just a few grams, to 20% the speed of light. If successful, they could reach Proxima b in about 20 years. It sounds plausible, but pushing even a small object to such speeds would require an energy output equivalent to a massive nuclear power plant running at full capacity, and a deviation of just a few millionths of a degree could send the craft billions of kilometers off course. A planet at the perfect Goldilocks distance, possibly harboring water, yet scorched by flares from its red dwarf star, radiation hundreds of times stronger than the sun's. A planet the same size as Earth, yet tidally locked, with one half melting under eternal heat and the other frozen in perpetual darkness. Then, in 2023, the James Webb Space Telescope opened a new chapter. With its superior infrared vision, Webb not only saw these planets but smelled their atmospheres. It detected water vapor, methane, carbon dioxide, even traces that could hint at biological reactions. But it was here that Webb's first data puzzled scientists more than it thrilled them. Some planets that should have stable climates were too hot. Others that couldn't possibly have water showed signs of moisture. Yet perhaps the greatest paradox lies not out there, but within ourselves. For even after creating machines that can see across billions of light years, humanity still does not understand the meaning of its own existence. We search for planets with life while destroying the only living planet we know, Earth, every single day. We dream of reaching Proxima Centauri, yet cannot preserve the fragile ecological balance beneath our feet. The strange worlds beyond may serve not as promises, but as reminders. They force us to confront a question no telescope can answer. Is human intelligence truly capable of transcending its own nature, its instinct for self-destruction? If Pluto is the ultimate test of physical limits within the solar system's backyard, then Proxima Centauri is the mirror that reflects the boundary of all humanity. So close, it feels like we could reach out and touch it, yet in truth, it is farther than imagination itself. We know its position precisely, its orbit, its mass, its brightness, even the planet that circles it. Proxima b, believed to contain liquid water, an environment where life could possibly exist. But all that knowledge is just light that left that star long ago. It means that every time we look at Proxima Centauri, we are looking into the past. And that past lies 4.24 light years away, nearly 40 trillion kilometers, a number so vast it defeats human imagination. That distance may sound close when we speak of stars, but if we launched New Horizons, the fastest spacecraft ever built by humans, in that direction, it would need 80,000 years to arrive. In other words, if we had launched it during the time when Neanderthals still walked the Earth. Only now would it be reaching the first rays of light from Proxima. Even if we accelerated it 100-fold, the journey would still take more than 400 years, longer than the lifespan of any civilization that has ever existed. And here lies the first great paradox. The nearest star is also the one we cannot reach. When Einstein announced his special theory of relativity in 1905, he not only opened a new age of physics, he also, perhaps unknowingly, locked humanity inside the cage of light speed. Nothing with mass can ever reach or surpass the speed of light, because to do so would require infinite energy. In other words, to reach Proxima Centauri within a human lifetime, we would have to break the very fabric of reality itself. But in 2016, the breakthrough Starshot project was born, backed by Stephen Hawking and physicist Yuri Milner. The plan envisioned thousands of nanospacecraft, each weighing only a few grams, propelled by gigawatt-class laser beams from Earth, accelerating to 20% of the speed of light. That velocity, they could reach the Alpha Centauri system in just 20 years. A beautiful and insane idea. Because while lasers can send the craft forward, no one knows how to stop it. There is no fuel, no braking system. We can send them out, but we cannot bring them back. Just like New Horizons once flew past Pluto without stopping, Starshot may be nothing more than a quick, radiant brush with the cosmic door, before vanishing into the void. And the true tragedy is this: even at 20% the speed of light, a single dust particle could unleash the energy of a small nuclear explosion upon impact. No known material today is strong enough to withstand that. Each cubic meter of interstellar space contains dozens of microscopic dust particles, and at that velocity, each one becomes a deadly bullet. The universe, seemingly empty, is in fact a vast invisible battlefield filled with death. Even more daunting, a minuscule deviation, a degree as small as 0.001 degrees at launch, could throw the spacecraft billions of kilometers off course by the time it arrives. We would not only need to shoot the star across light years of distance, but also predict its future position, knowing that its light takes years to reach us. Though technologically impossible for now, Proxima Centauri continues to hold a near religious fascination. around it. Astronomers have discovered Proxima b on a planet nearly the same mass as Earth, orbiting within the liquid water zone, where life, at least as we understand it, might exist. But the truth is, Proxima Centauri is a red dwarf, a small, cooler, and extremely unstable type of star. It emits intense ultraviolet and X-ray radiation, hundreds of times stronger than what Earth has ever endured. Each stellar storm could strip away Proxima b's atmosphere in just a few million years, blowing off every molecule of water and oxygen. A research team from the University of Geneva in 2020, using data from the espresso spectrograph on the Very Large Telescope, confirmed the existence of Proxima b. They also suspected a second planet, Proxima c, larger and farther out, possibly so cold that its entire surface is frozen. A frozen world orbiting a red sun? The nearest star, the most Earth-like planet, and yet, perhaps, the harshest place imaginable. Scientists can calculate the mass, orbit, and even the possible atmosphere of Proxima b, but they cannot see it. All the data we have are tiny fluctuations in the light of its parent star, measured through the Doppler effect. Every figure represents billions of calculations, born from ancient photons that traveled across light years to strike our sensors. All we truly see is the bent light of the past. Perhaps, in the moment we send our first nanoship toward Proxima, somewhere out there, another civilization, if it exists, is doing the same, sending light toward us. Two signals crossing paths in the void, never touching, yet leaving behind one eternal question. Are we truly alone, or just too slow to meet each other? Proxima Centauri teaches us a profound lesson. Human progress is not limited by intelligence, but by time and energy. Every dream of reaching the stars must be paid for in generations of waiting. If Pluto is the harsh challenge within the backyard of our solar system, and Proxima Centauri is the invisible wall separating us from the stars, then the true barrier lies not merely in distance or speed. Every dream of interstellar travel shatters before Einstein's special theory of relativity. The speed of light, 299,792 kilometers per second, is not a target to be achieved, but an absolute limit. No object with mass can ever reach or surpass it. As an object accelerates, its mass increases exponentially. To reach the speed of light, the required energy becomes infinite. The closer we get to light, the more tightly we are bound by the laws of physics, imprisoned by limits the universe set billions of years ago. Even aiming for just 10% of light speed, a fraction of the ultimate limit, is a nearly impossible challenge. To accelerate even a small spacecraft to that velocity, we would need energy equivalent to thousands of years of the entire Earth's electrical production. Imagine a civilization expending its millennia of progress just to push a tiny machine through the cosmic void. Would humanity ever be willing to sacrifice its entire planetary resources for a voyage to the stars? But energy is not the only problem. Interstellar space is far from empty. It is a sea of subtle violence. Cosmic radiation, composed of high-energy particles from supernovae and black holes, can destroy human DNA and permanently damage electronics. Interstellar dust is a silent but merciless enemy, a particle smaller than a pinhead. Colliding with a ship moving at 20% the speed of light carries energy equivalent to a small nuclear explosion, enough to tear sails apart or puncture the hull. The universe, though seemingly tranquil, is a high-speed battlefield where every object is prey to the laws of physics. The challenge runs even deeper with time and durability. A journey to Proxima Centauri would last hundreds, even thousands of years. No material on Earth could survive such a span in that environment. Every metal, every synthetic compound would gradually degrade, erode, and crack under the constant assault of radiation and interstellar particles. The spacecraft would become a drifting wreck long before ever reaching its destination. Modern science can calculate design and predict. We can imagine a nano spacecraft, like in the breakthrough Starshot project, sailing on laser energy at 20% the speed of light, reaching Proxima Centauri in just about 20 years. But even if the theory works, the technology remains an abyss. How can a nanolight sail survive collisions with interstellar dust without disintegrating? How can it maintain trajectory in a weightless void where even a microscopic impact could send it billions of kilometers off course? And more importantly, how can we collect data when every signal sent back to Earth would take over 4 years just to arrive, creating a delay beyond human patience? The irony is that every step we take toward those distant planets reveals new paradoxes. Proxima b, potentially harboring liquid water within its habitable zone, orbits a star that unleashes massive radiation storms capable of stripping away its atmosphere within geological time. A planet that seems perfect for life may, in truth, be a cruel testing ground, where every flare is a reminder that life beyond Earth may be rarer than we dare to believe. Where a place seems ideal, it may be a trap. Where it appears lifeless, it could hide opportunity. The so-called super-Earths, some with oceans hundreds of kilometers deep and pressures thousands of times that of Earth, prove this paradox. Some of them have magnetic fields hundreds of times stronger than Earth's, strong enough to protect their atmospheres, but unpredictable enough to make any forecast of climate or oceans uncertain. LHS 1140b, located 40 light-years away, is considered one of the best candidates for habitability. But even at our fastest speed today, humanity would need over 200,000 years to reach it. And perhaps the most profound reflection of all, science not only brings our dreams closer to reality, it also reveals our helplessness. Each new planet discovered does not open a door. It reminds us that the universe is millions of times greater than our reach. Every piece of data from James Webb, TESS, or Kepler is a cold echo from afar. Those brilliant worlds are nothing but frozen lights. Places where life, if it exists, endures silently under the relentless rule of physics. The exoplanets beyond, from scorching gas giants to icy rocky worlds, are not just distant points of light. Mirrors reflecting the deepest longing of humanity. If the previous section revealed the physical and technological walls that separate us from the stars, then now we must confront a deeper, more intimate challenge: time and human perception. Interstellar space may be cold and radiation may be destructive, but the true barrier lies within our own biology, psychology, and society. Imagine a journey to Proxima Centauri, the nearest star beyond the Sun. The distance of 4.24 light-years seems small on an astronomical map. Yet in reality, with any existing technology, the voyage would take centuries. This is no longer an ordinary journey, it is a voyage across generations, where those who depart will die long before their descendants ever glimpse the destination. Generations born aboard the ship, never having breathed natural air or seen Earth, would live out their lives inside a cold steel vessel drifting through infinite space. Here arises a profound psychological and social paradox. How can hope, purpose, and order be maintained within a closed community where every effort is devoted to a goal that none will ever witness? Theoretical models of generation ships have been proposed by scientists since the 1970s. But most have concluded that sustaining a small society on a centuries-long voyage is almost impossible. An unprecedented moral and governance challenge in human history. Yet the problem extends beyond society itself. Human perception also builds an invisible wall. We are born and live according to the rhythm of a lifetime. We measure time in weeks, months, and years, rarely imagining spans that stretch beyond personal existence. Meanwhile, the universe moves in the rhythm of billions of years. Earth is 4.5 billion years old. Proxima Centauri is just 4.24 light-years away. The number seems small, but in the rhythm of human life, it is a temporal abyss. 1. our minds and biology cannot fully grasp. We know the distances, we can calculate orbits, and we can even dream of the stars. Yet it is our own consciousness and biology that make those dreams nearly impossible. Humanity is a species born to live and die by the cycle of sunrise and sunset. To reach the stars, we would not only need powerful spacecraft, we would need to alter our very biological, psychological, and perceptual nature. They remind us that, in our quest for exploration, the true frontier is not made of planets or stars, but of endurance, awareness, and patience. Earth is 4.5 billion years old. Proxima Centauri is only 4.24 light years away. The distance may be small on a cosmic scale, but it lies far beyond our biological, psychological, and social limits. No material or technology can replace the ability to preserve culture, education, and social values across generations, far from Earth. A machine may endure, but a biological and spiritual society may not. Those planets and stars are not merely physical destinations. They are mirrors reflecting the intelligence, ambition, and fragility of humankind. In the silence and mystery of the space between stars, humanity learns that to venture beyond the solar system, we must first expand the boundaries of perception. To learn endurance in solitude, to find meaning in time unending, and to discover purpose even before touching the distant stars. Pluto and Proxima Centauri stand as two opposing symbols. Not merely representations of physical distance, but reflections of the deepest limits of human knowledge and existence. On one side lies Pluto, the frozen world at the edge of the solar system, close enough to see, yet requiring a journey lasting decades to reach. A voyage in which even our fastest probe can only glance past it in the blink of cosmic time. On the other side, Proxima Centauri, the nearest star beyond the Sun, 4.24 light-years away, stands as an unbreachable wall of physics, defying even the boldest ideas of our age. From Pluto's perspective, the Sun appears only as a dim point in a black sky, a faint shimmer in the endless void. Likewise, Proxima Centauri is but a tiny glint in the interstellar darkness. Both, though at opposite extremes of space, mirror the same truth: the limits of human perception, control, and conquest. They are harsh reminders that no matter how far science and technology advance, we remain bound by the laws of nature, by hostile environments, and by the confines of our own awareness. We once believed that reaching another planet or star was merely a matter of speed, engines, or fuel. Every small step forward, every solitary discovery among distant planets, marks a greater leap in awareness and comprehension for humankind. In the light of these two extremes, Pluto and Proxima Centauri become dual symbols, both scientific challenges and philosophical reminders. They teach us that science is not only about measuring and discovering, but about recognizing both our potential and our limits. And until we transcend the barriers of mind and biology, they will remain distant stars, cold yet necessary reminders of where we stand, what we long for, and the next steps humanity must take to one day truly reach the stars. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.